So this is Professor Thompson. I'm going to do an example from 2.8 and talk a bit more about differentials. So the idea of a differential, if I have dy dx equals f prime of x, then differential dy, that's the rate of change, or the measure of change in the tangent line. That's just f prime of x times dx, and that's the measure of the change in x along the tangent line. And if dx isn't too small, then the rate of change of the measure of change of the function is about the same. So, for example, here's a tangent line to a graph, and then there's the tangent points. And if I go the same distance, dx and delta x would be the same. Delta is on the function, and dx is on the tangent line. Then the overall, that whole length of that line is dx, and the little part is delta x. And that's a big difference, but if I go really close to the tangent point, they're about the same. So that's the idea of what we're doing here. We're going to use differentials to have an easy way to solve for the change of a function. And you can do this when to figure out errors in measurements. So let me do number 21 here in the section. So it says the edge of a cube was measured to be 30 centimeters, but the area measurement is up to 0.1 centimeter. Possible error of 0.1 centimeters. And they want to know what's the maximum possible error, the relative error, and the percentage error of the volume and the surface area. So we'll do volume first. Well, the volume of a cube, V, is A cubed. So if A is the sides length, then this 30 centimeters, that's A, and the possible error is dA, right? That's how much A can change. So I'm going to take the derivative with respect to A, and I get dV dA equals 3A squared. I don't put anything else because A is the respective variable. So this is kind of like the previous sections before 2.7. And I can solve for dV by writing dV equals 3A squared dA. And let's see. A was given to be measured to be 30, and dA was 0.1. So this is 2,700 times 0.1, which is 270 centimeters cubed. So that's as bad as the error in the volume can be because I put the worst possible error in for dA. Okay, so that is the maximum possible error of dV. So let me go ahead and write that on the next page. So I have dV is 270 centimeters cubed. And remember that A was 30 and dA was 0.1. So to put this in perspective, it really helps to think about how big the overall cube is. And so I should take dV divided by the total volume. And so this is 270 divided by the volume of the cube, which would just be 30 cubed. So this is 270 divided by 27,000. And so this number is just 0.01. And so that's called the relative error. That's dV divided by V is 0.01. And changing that to a percentage is the percentage error. And so that's going to be 1% if I just move the decimal over 2 spots. So even though it looks like 270 centimeters cubed is a big problem, it's really only a 1% percentage error. Okay, so now I can do the same thing with surface area. So I'll call the surface area S, and each face of a cube has area A squared, and there's 6 of them, so this is 6A squared. So I take the derivative ds over dA, because I'm taking the derivative with respect to A, and then I get 12A. And I solve for ds, and I have these values. I know that A was 30 and dA was 0.1. So this is 360 times 0.1, which is 36 centimeters squared, because this is area. Okay, so that's the error and surface area. And now I want to get the relative error. So I want ds divided by s is 36 divided by 6. A is 30, so squared. And here, this comes out to be 0.006. And so the percentage error then, I moved the decimal twice, is 0.6%. So this is my relative error, and this is my percentage error. And it's less than the volume's percentage error because surface area only has a squared, right? Whereas the volume had a cubed. So that error was being multiplied every time you had another factor of a. That's why the surface area doesn't have as much error.